Okay, hello everyone. My name is Tae-Sung from Dankook University in Korea. Today I'm going to talk about structural performance of precast and cast-in-place composite concrete beams with dapped ends. Actually, this study was conducted in contributions my PhD students, Mr. Seung Lee in Dankook University. And before I start my presentation, I'd like to acknowledge that the title of my presentation was changed. Actually, there was a mistake in delivering my presentation information. I apologize for that. Okay, this is the content of the presentation, and this slide shows a precast concrete frame flow system developed for underground parking garage in Korea. Actually, this system has a planar T-frames supported by staggered walls. Actually, using this kind of staggered walls, we can reduce span length. So we also reduce beam moments on the gravity loads. And this is the precast construction process. And on your right, you can see a precast beam connection. And these two photos were taken in a construction site in Korea, where the proposed precast system was used. And in this slide, you see the details of the precast beam connection. And actually, this connection is in mid-span, so it is very important to secure the structural performance at the beam connection. So we used the three different strategies. The first, to enhance the structural integrity at the connection, we used the precast and cast-in-place the composite concrete joint. And second, we actually used a depth and detail for precast beam elements, so the sub-beam can be mounted on top of the main beam. And third, a groove detail was introduced at the beam ends, so that the cast-in-place concrete topping can be easily engaged with the precast elements. And in this system, my presentation focuses on the shear strengths of this kind of composite concrete beams, and there are two shear strengths that needs to be addressed. The first one is the shear strength of composite concrete section, and actually, according to the literature, when we calculate this kind of strength, we can use the same design equations as those for monolithic reinforced concrete sections. And the second one is the shear strength of composite concrete depth ends, and I think in this case we have to use a kind of linear analysis along the critical crack line, or as you can see here on top at the top, or we can use the conventional strata and tie models for depth ends. So this, so the research objective is to investigate the shear strength of composite concrete beams, and this study focuses on the composite section of precast and the cast-in-place concrete. At the same time, this study focuses on the depth ends with groove detail. Okay, from now on, I'm going to introduce a test program. And in this slide, you see a simple beam with the depth end in the left span. And on your right, you see a groove detail used for the depth end. And you also see some special reinforcement used for the groove. And actually, a conventional strata and tie model used to design this kind of composite concrete depth ends, and on your right is the reinforcement detail for the depth ends. And as you can see here, distributed stirrups were used to increase the shear strength of this kind of composite concrete depth ends. And in this test program, the primary test variable was the beam depth. So this slide shows the reinforcement details of the first three specimens with a depth of 600 millimeters, and the precast depth was 450, and the casting price depth was 150. And this slide shows the reinforcement details of the second 3 specimens with a depth of 450 millimeters. The precast depth was reduced to 300, and the casting price depth was 150. And if you take a look at the stirrup spacings in the left and the right spans, and in the left spans with the depth and the detail, you see more stirrups are placed. This means that the left span can be stronger than the right span without depth end. This slide shows the test results of the first 3 specimens with a depth of 600 millimeters. On your left, the cyclic, force deformation curves obtained from the test, and each color indicates specimens with different groove details, and clearly grooves reduce the stiffness after flexural ending. And on your right the crack patterns of the specimens, and you don't see any major cracks. This means actually depth and shear strengths were much stronger than my time order strength. So unfortunately, test ended before failure due to the lack of the loading capacity. And this is the test results of the second 3 specimens with a depth of 450 millimeters, and 2 of them failed due to typical shear failure in the right span without depth end, and the last one showed flexural yielding in mid span. And this slide shows the strap strains obtained near the depth end, and in these graphs, each color indicates the strap locations like G1, G2, G3, and G4 here. Okay, and horizontal axis is center deflection, and the vertical axis is strap strain. And as you can see here in the test results, although cracks were not obvious around the reentrant corner, the magnitudes of measured strap strains decreased as the distance from the corner increased. Okay, let's move on to nominal strengths. And first, I'm going to talk about the flexural and the shear strengths of composite concrete sections. And this slide shows the cracking along the concrete interface between precast and the cast in place. And actually, there were little or no cracking along the concrete interface. This indicates that maybe we can calculate the flexural and the shear strengths of a composite concrete section by using conventional design methods for the monolithic reinforced concrete. And this slide shows how to calculate the flexural and the shear strengths of composite sections. And this slide compares the test strengths with the nominal strengths, and specimens number 4 to number 6 at the bottom, highlighted in blue, were estimated to fail in shear, and the nominal shear strength was very close to the test strengths. On the other hand, for specimens number 1 to 3 at the top, actually their flexural and shear strengths were much greater than their test strengths. And actually, when we record the test results, actually the 3 specimens at the top did not fail until test ended due to the lack of the loading capacity. And okay, the second one is the shear strength of the depth ends, and conventional strut and time models significantly underestimated the shear strength by about 50%. So I investigated limit analysis based on the critical crack, and this critical crack means the diagonal shear crack initiating from the reentrant corner. And this is the proposed limit analysis based on the critical crack. And on your left, by summing all the contributions from the strop crossing the critical crack, we can calculate the depth and the shear strength. And in this case, we have to calculate the crack angle and the number of strops crossing the cracks with accuracy. And in this free body diagram, we can take force equilibrium, and by solving equilibrium equations, we can get this kind of depth and the shear strength equation. And in this equation, the flexural and the shear strength of the composite depth section are denoted as V and M are included. And actually, the composite depth end means the section which is much smaller than the beam composite section. You can see the composite depth section on your right. And the strength of these flexure and shear strength of this composite depth section can be calculated by using the conventional design methods. And in this slide, the calculated depth and the shear strengths were compared with the test results, and these strengths were much greater than the test strengths. And actually, the reason is that actually none of these 6 specimens did not fail in depth and the shear failure. And this means that to verify these equations, we have to do some kind of finite element analysis. And this slide shows the finite element modeling for the specimens. And the slide shows the comparisons between the finite element analysis and test, and you see good agreements between the two. And in particular, the finite element analysis estimated the detailed behavior at the depth and the corner, actually, such as critical crack opening and strop stresses concentrating near the corner. And by using the finite element modeling validated in the previous slides, we reanalyzed the specimens by increasing reinforcement areas other than the depth and regions. We wanted to see depth and shear failure from the analysis, and red lines indicates the test result, and the horizontal dashed line indicates the shear strength calculated by the proposed limit analysis, and you see the good agreements between the two. And this slide shows the strop stresses obtained from the finite element analysis, and you also see the critical crack planes calculated from the proposed limited analysis, and this figure clearly demonstrates that the proposed limited analysis can capable of predicting the shear strength of composite concrete depth and connection. I'm going to write a presentation with this slide. Thank you.